So here's the thing about integrals. In order to do the integral, we have to compute the reverse of the derivative. That's the key thing about the fundamental theorem of calculus, and we'll get into that. But one of the key skills is you have to be able to reverse the derivative. Okay, so let's just talk about what that means. What that means is we're going backwards in our table. If we're given something on the derivative side, we want to get what we call the antiderivative. That is reversing the process of the derivative here. And this can be a little tricky. Like a lot of times it's just the table because you've been training your mind to be like, this is what a derivative is. And an antiderivative is we are going to reverse that process. Now, a couple of things that are kind of interesting. It's a little bit hard to reverse all of them. Like we can't reverse quotient rule, product rule, chain rule, or we kind of can, but it's not easy to reverse those things directly. So in the beginning, we're just going to talk about reversing just core functions. The other thing, because we're reversing the derivatives, it has the same properties as derivatives. That means it's linear. What that means by linear is like I can take the antiderivative of each function separately if I'm adding them up. All right, and so we'll go through a few examples and see like that. Now, one of the tricky rules is power rule. Power rule is a little bit tricky to kind of do in your head. The way I like to think of it as a completely separate rule. It's just you kind of just going to make it a new rule and not try to reverse the derivative so much. But just think like we're going to add 1 to the exponent and divide by that new exponent. So let me give you an example here. If I had, say, x squared or x squared as my function, and I wanted to know what's the antiderivative of this? What's the integral of x squared? In other words, when I take the derivative, I should get back to x squared. The way you want to do the power rule is you're going to add 1 to the exponent, and then you're going to divide by that new exponent, and you're going to get 1/3 x cubed here. Okay? And the whole idea here is this thing, when I take the derivative, what is the derivative of this? The derivative of this is going to be 1/3 times 3x squared, right? Because by power rule, and that's going to, the 1/3 and the 3 will cancel, and I just get x squared. And that's what I want. I want to find a function where when I take the derivative, I get this thing. So it's kind of the reverse process of doing the derivative. Okay? Now, here's the thing that's interesting about antiderivatives is they're not unique. That is, any function, when I add a constant, will have the same derivative. For example, if I add in 5 here, and I take the derivative, I also get x squared. So this is kind of interesting. They are not always unique. So a lot of times when we do an antiderivative, we can add any constant we want. So in other words, instead of saying plus 5, we can say plus, say, c. Any constant will do because if I include a constant, the derivative will still give me that function there. Okay, so and that's the example here. These two functions, they differ only by a constant. It's plus 3 versus plus 1. They have the same derivative, 2x. And so when we do antiderivatives, not unique. So a lot of times you have to add in this plus c when you're doing an antiderivative. So let's do a quick example. Let's do the antiderivative of, say, cosine x plus sine x minus 1 over x. Okay? And this one, you're again trying to figure out, and you can do this because you're allowed to do the integral of each one separately because you can do the derivatives of each one separately when you're adding them up. Oh, let's put a number in front. Let's put like a 2 here or something like that. 2 cosine, oh actually, let me put it in black. 2 cosine of x. Okay, so what derivative would give me cosine of x is sine of x, right? So 2 sine of x, because the derivative of sine would give me that cosine there. Okay, what derivative will give me sine? Well, I might want to say cosine of x. However, the derivative of cosine is negative sine. So we're going to put a minus sign here because then the negative cosine, the derivative, will give me positive sine x. So you got to be very careful here is that you might have to do some signs or some constants in there. Minus, what derivative gives me 1 over x? That is natural log of x over here. So then we would say minus natural log of x. And again, you can confirm this by taking the derivative of this thing here and confirming that it matches that thing. Okay? And then we always put a plus c here to indicate that the antiderivative is not unique. This is not the only thing that would give me this derivative. I can add some constant to it as well. Okay, so now we're going to do some more examples related to that, doing these kinds of reversing that derivative process or the antiderivative. So now we're going to be getting into integration. And the most common way you're going to do an integral is by doing an antiderivative. Antiderivative is kind of doing the backwards of a derivative. And for a lot of these, what you're simply going to do is going to do the reverse of the rule that you would to take the derivative of. So for example, for power rule, when I take the derivative, what I do is I multiply and I subtract 1. But to do the integral instead, the integral of x to the n dx, I'm going to add 1, and I'm going to divide by n plus 1. And I think of it as I add 1, I divide by that new exponent. So for example, for here, one of the things I can do is I can leave the 3 alone, and then just do the integral of x cubed dx. And so this is going to be 3x to the 4th over 4, which is 3/4 x to the 4th. The other thing about this is I always have to add a constant of integration for these indefinite integrals. And that's because you want to think of it as if I take the derivative of this, I get back to here. And the derivative of the constant is always 0. So one thing that's a key point of integrals is that they're actually not unique. They can be vertically shifted by some arbitrary constant c. Okay, let's look at this one. This one I'm going to be doing 10x squared. So the integral is going to be 10 x cubed divided by 3 minus 2x. And you can always just simply take the derivative and make sure that it works out to be the same. Once you have your derivatives down, you just simply take the derivative and see if it matches. So if I take the derivative of this, I'm going to get 10x squared and then just 2. So this would be, just to simplify a little bit, 10/3 x cubed minus 2x. And then don't forget the integral constant. Because again, this value can be any value, and it would still give me this as the derivative. Okay. Integral of 1 is just s plus c, or whatever variable it is. In this case, ds is our s is our variable of integration. This one I write as 3t to the negative 2 dt. And so then I can apply my power rule. I'm going to add 1 to the exponent. I'm going to divide by that exponent. So this would be negative 3 over t plus c. Secant squared theta, that's just what rule we know. That's tangent theta. Don't forget your plus c. You will definitely be docked for not having plus c. Either your teacher will dock you, or on the AP exam or any examination you take, you'll definitely get docked. Secant tangent. This is what you have to remember is the integral of this one is the derivative. This is secant x, and this is minus cosecant x plus c. And that's because the derivative of secant x is secant x tan x, and the derivative of cosecant is negative cosecant x cotangent x. That's why I put a minus sign here, because when I do the derivative, this minus the minus sign from this derivative will cancel and become a positive. 3 to the t. Remember, derivative of 3 to the t is 3 to the t ln 3. So to do it backwards, I just divide by the ln of 3. Because if I do the derivative of this, I'm going to multiply by the ln of 3, and that will cancel with that, right? And that will get me back to 3. Yeah. This one, there's a couple of ways you can do this. You could kind of infer, like one thing you could do is, you could do 1/3 2t plus 3 to the cubed. But the problem with this approach is that you're going to be off a little bit, because if I take the derivative of this, by chain rule, I have to multiply by the derivative of the inside and make it 2 by 2. So to compensate for that, I can divide by 2, and that would make this 1/6 2t plus 3 cubed plus c. I recommend you kind of learn that sort of idea. There are more formal techniques we call U substitution that will help you formalize that. But if you can kind of intuitively do like quick chain rule properties, or handling the fact that chain rule will change the answer, that would be useful. This one I want to use is not the, I want to simplify it to be x to the 5th dx by adding the exponents. And so this would be 1/6 x to the 6th plus c. Right, so I add 1 to the exponent and I divide by that exponent. A dx, this is assuming a is a constant, so this would just be ax plus c, because the derivative of this would just be a. So now we're going to be adding in initial value problems, and this has to do with the constant of integration. So in general, to find f of x, I just simply do the antiderivative of this. the antiderivative of sine is cosine, but I have to put a minus sign because the derivative of cosine is actually negative sine. So I need a negative sign there, like that. So that's just me doing the integral, or the antiderivative of sine x. But this allows you to find what the constant is. We call this the initial value. Because if I plug in 0 here, I'm going to get negative cosine of 0 plus c. That's negative 1 plus c. And this tells us that this negative 1 plus c ought to be equal to 2. And hence, c would have to equal 3. So our exact answer, our particular solution, would be negative cosine x plus 3. Okay, so the initial value is just a way that you can use the initial value to solve for the exact value of c. Okay, here I'm going to do the antiderivative again. The antiderivative of this is x to the fourth, because x to the fourth, the derivative of that is 4x cubed minus x cubed. And then a plus c here, and then I know f of negative 1 is has to equal 9, but plugging in negative 1 here, that's going to be negative 1 to the fourth minus negative 1 cubed plus c. Negative 1 to the fourth is positive 1 minus negative 1 cubed is negative 1 plus c. And that's 2 plus c is 9, so that means c has to equal 7. And so then my answer is f of x is equal to x to the fourth minus x to the cubed plus 7. Okay. Here, to do the antiderivative, I know that in general it's 7 to the x. If I were to take the derivative of this, I'd have to multiply by the natural log of 7. So to undo that, I got to divide by the natural log of 7, and then plus c. And then I know f of 2 has to equal 1, and that's 7 squared over ln of 7 plus c. That's equal to 49 over ln of 7 plus c, and so that means c has to equal 1 minus 49 over the natural log of 7. And so our f of x is 7 to the x over ln of 7 plus 1 minus 49 over ln of 7. Okay. Similar thing here. Here I have a second derivative. Okay, so first I do an antiderivative to find the first derivative. That would be 7x squared over 2 plus c. But they gave us, I can find c because they gave us what the first derivative ought to be at 1. So the f prime at 1 is going to be 7 over 2 plus c. That has to equal negative 1. So c would equal negative 1 minus 7 halves. And that's negative 9 halves. So that means this is equal to 7x squared over 2 minus 9 halves. And now I can do the antiderivative of this one by to find f of x. So this I'm going to do 7x cubed over 2 times 3 is 6 minus 9 halves x, and then here plus a constant. And now I'm going to use this initial value to solve for this constant, because I know f of 1 would be 7/6 minus 9 halves plus c, and that has to equal 10. So this would be 27 over 6. And then I subtract that, that's minus 20 over 6 plus c is equal to 10. And so that means c would have to equal 10 plus 10 over 3. 20 over 6 is 10 over 3, which is 40 over 3. So our solution then is f of x is equal to 7/6 x cubed minus 9 halves x plus 40 over 3. Okay, same thing here. First, I find the first derivative by taking the antiderivative of the second derivative. So that's cosine theta. I got to do a negative sign, though, because the derivative of cosine is actually negative sign. So I got to make sure I have a negative sign there. And so then, using this, I can find the constant of integration. Pi would be negative cosine of pi plus c. Negative cosine of pi is negative 1, so that makes it 1, positive 1. Plus c is equal to 2, so that's c equals to 1. So this is negative cosine of theta plus 1. And now I can find f of theta by taking the antiderivative of this, and I would get negative sine theta plus c. And I know that f of pi has to equal 4, so that's negative sine of pi plus c is equal to 4. Sine of pi is just 0, So that means c is equal to 4 minus pi. And so my f of theta would then be negative sine theta plus 4 minus pi. Okay. Last one here. So we're going to do second derivative is 0. That means the first derivative, the antiderivative of 0 is just 0, but I gotta add my constant plus c here, 0 plus c. And I know f prime at 1 has to equal 3. That has to equal c, so that means c is equal to 3. So f prime is equal to 3. And so the antiderivative of that has to be 3x plus c. F of 1 has to equal 1 for this initial value. And that's equal to 3 plus c, plugging x equals 1 into there. And so that means c would have to equal negative 2. And so my f of x would then equal 3x minus 2.